Alright, so now that you are clear with all the states that you need to look for, so how are you going to solve this in order to get your H1, right? In order to get your H1, H4, H2, and H3. Okay. So the tricks is like this. Remember when we learned about your pure substance, I said that when you wanted to read your property table, you need to have two known value. So in this case, you always start with the states, right? State 1, 2, 3, 4. You always start with the states that have two known value. Okay, that's the trick, so that when you solve your problem, it is much easier and quicker. Okay, so in this case, it happens to be your state 1 has two known value, which is you have the pressure 3 megapascal as well as the temperature, which is 300 degrees C. So let's start with that first. Okay, so you have state 1, which is your P1 is equal to 3 megapascal, and then temperature 1 is equal to 300 degrees C. So you will need to read your property table, your property from table A6, right? So what are we looking for? We are looking for your H1 because it will be needed in finding your Q in here, as well as your work in. Okay. And also, you are going to need the value of your S1, right? The value of your S1. Why? Right? We will see later when we're trying to solve for your state 2, we will see why are you going to need your S1. So open up your property table and read from your property table A6. When the pressure is 3 megapascal with 300 degrees C, what will be your H and your S value? Now let's move to the next state, which is your state 2. So you know that state 2, you're given your pressure P2 is equal to 50 kilopascal, right? So now the other things that you know about state 2 is that your S2 is equal to your S1. Okay. So recall back, in order to read your property table, you need two known value. Now, why is that your S2 is equal to S1? Okay. Remember, we are trying to solve the problem of simple, ideal Rankine cycle. So when it is ideal, recall back, we learned about entropy before. What does entropy means? It is actually ideal cycle where the entropy value of your inlet is equal to the entropy value at your outlet. Right? What does it mean actually? It means that you don't have fluid friction that contribute to heat. Right? We will see later as we progress. You are going to have some modifications, right? And you are going to have actual Rankine cycle, reheat Rankine cycle, as well as regenerative Rankine cycle. So you are going to compare the ideally part with the actual part. That's why we learn these entropy things before we get into this steam power plant chapter. Okay. So given to you pressure and this entropy value, and because in ideal simple Rankine cycle, the outlet of your turbine must be in mixture region. So basically this value at state 2, you are going to read it from table A5, right? So you will need to find your H2. What is your H2? But before you can do that, you will need your value of your X. Where do you get your value of your X? It's from this equation. Okay, so once you obtain the value of your X, then you will plug into the same equation, but you're going to change this with H in order for you to get your H2 value here. Okay, so you read the property of SFG, your H2 your HF plus X2 HFG, okay, also from table E5. Okay. Alright, I'm not going to show you in detail how to calculate this, but you should obtain the value of X is this one and the value of H2 is this much based on this equation. Okay. Alright, now that you have already solved for your state 1 and 2, let's continue to solve for your state 3. So in your state 3, you know that your P3 is equal to 50 kilopascal and that it is fully saturated liquid. So your your H3 is equal to HF at 50 kilopascal, right? So basically you are going to read this from your table E5. Okay, and there's another value that you need, which is this one, your V3. Okay, specific volume at 3, which is equal to VF also, right? And you are going to read it from table A5. For the work of your pump, it's either you are going to use the enthalpy value or also you can make use of this one. Okay, recall back on the topic of fluid motions where you have specific volume and your pressure, right, will give you a workflow. Okay, because in this case your pump, the function is to feed back this fully liquid get back into your boiler, right, so that you can continue the cycle back. Okay, it will heat it up into your turbine, get out from your turbine into your condenser, and this will repeat the cycle. So basically you are going to have the same volume but with a different pressure. Okay, and it will give you workflow, right? Workflow over here. Oh, I need to repair this. This is work out and work in. I have repaired it. Sorry about this notation, this wrong notation before, right? So your work in must be your pump, your work out must be your turbine. Okay, so therefore you are going to need your V3 here. Okay, and the volume of 3 and 4 is the same. It's just that the pressure will be different because of the function of pump is just to increase the flow. Okay, next we're going to solve for state 4 where your state 4 is equal to 3 megapascal, right? And your V4 is equal to your V3. Okay, so you need to find your H4, remember? In order to solve for this one and this one, you will need your H4. So what is your H4? Okay, so you can make use of this equation over here in order to gain your H4. Okay, so let's rewrite the equation. So you are going to have H4 minus your H3 is actually equal to specific volume at 3, P4 minus your P3. So you have V3 from here, you have H3 from here, you have P4, it's already given to you, this is the constant pressure line, P4, and P3, this is the constant pressure line of your P3, right? So finally you will get your rearrange all this value and you will get your H4. So finally you will get your H4 as this one. Okay, now that you get all the value of all state, H1, H2, H3 and H4, so now you can solve for the first one, which is to find your thermal efficiency. Alright, now that you have all the value of H that you need, and not to forget in your question it's already given your m dot, which is 35 kilogram per second. So the first one we are going to solve for your thermal cycle efficiency, and then we are going to get the work net in kilowatt or kilojoule per second. Alright, if you see this equation over here, Q in is the same with Q in, so it can be simplified with your mu thermal or thermal cycle efficiency could be 1 minus your Q out over your Q in, right? So in this case, because you don't have your mass, it's just that in kilojoule per kg, so you need to have 1 minus your Q out over your Q in. It is a specific heats, right? So your Q out is in between state 2 and 3, okay, and your Q in is between state 1 and 4, okay. So we rewrite this one. Now your mu thermal is equal to 1 minus with your Q out in between H2 minus your H3 over your Q in, which is between H1 minus your H4. So finally you will get, to forget, you need to times with 100 because we are talking about percentage here, okay. You will get about 27.1% the thermal cycle efficiency. So let's look at your work net. So for your work net, because it wants to have a power, so you need to times with your m dot, which is 35 kilogram per second, and it happens between your work of your turbine minus with the work of your pump, where this is the work of your turbine and this is the work of your pump. Work in and your work out, okay. So you plug into this equation, finally you will get this much value, right? So you see here the thermal cycle efficiency is very, very low, not even reach 50%. It is 1/4 from 100%, meaning that, what does it mean here, right? Remember that the steps in seven steps in problem solving, you need to verify or discuss your findings here. Why is it that you get not more than 30%? Okay. So this is why in later chapter you will see that this Rankine cycle, simple ideal Rankine cycle, are going to have a few modifications, right? Where we name it as reheat Rankine, and then we are going to have regenerative Rankine, so that we are going to improve this thermal cycle efficiency. Okay, so that the whatever fuel that you burn inside your boiler to have this steam, right, which is your Q in, are going to be useful, right? If it's not 100%, it's going to be at least more than 50% useful to produce this desired work, which is to turn your turbine and produce electricity, right? So that's all for this simple ideal Rankine cycle problem solving. You need to try on a tutorial in that I placed in your MOOC. You need to try out that one. Okay, so then later we are going to move to the next stage, which is your actual simple Rankine cycle. Okay, thank you.